Hey, what's going on, Science 10s? Mr. Walton here. Today we're going to be talking about efficiency, one of the last topics of our physics unit here in Science 10. You can kind of define efficiency as the proportion or the percent of usable energy. It has to be usable, something you're looking for. The percent of usable energy that comes out of a system. And so what's going to happen is in every device or in every system that you use, you're going to be putting energy into it. It might be electrical energy, might be chemical energy, maybe you're burning something, you're using some sort of a fuel or whatever. But you're going to be putting in energy and you're trying to get out a certain type of energy. And every device that you use requires the energy input, but no device can convert 100% of its input energy into useful output energy. I mean, barring technically, we could say like an electric heater might be 100% efficient, but anyways, whatever, that's okay. So all devices will convert some of the input energy into a form of energy that isn't useful, so usually heat. So typically, we kind of talk about, we like to introduce this topic by talking about light bulbs. I know, super exciting, light bulbs, but we're going to talk about two different types of light bulbs. So we're going to talk about an incandescent light bulb, and then we're going to talk about an LED, otherwise known as a light emitting diode. So we could take a look at the incandescent light bulb, and an incandescent light bulb, you've seen it before. Whoa, man, that's terrible. Whoa, that's terrible. There we go, perfect. That's an incandescent light bulb. Now, it's got two electrodes inside of it, and then the electrodes are connected by a piece of tungsten, and we call that the element inside. And so the filament or the element inside of this light bulb, in an incandescent light bulb, usually only about 5% useful energy comes out of it. So we're going to have energy going in, usually that's electricity, right? And then we're going to have energy coming out, and only about 5% of the energy that we put in, we get out as useful energy. If you go up to an incandescent light bulb and you were to touch it, don't touch it. But if you were to touch it, you would notice, or put your hand close to it, you would notice that it's extremely hot. Now, what's the point of a light bulb? Is the point of a light bulb to give off heat? Well, maybe inside like an easy bake oven or something, but no, the point of a light bulb isn't to give off heat. The point of a light bulb is to give off a light. That's what we care about. Whereas if we were to look at an LED light bulb, okay, an LED light bulb shaped pretty much the same way. Blah, 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 blah. Perfect. Okay, but in here, there's going to be some housing that has an LED. And so I don't even really know what it looks like on the inside because I've never taken one out. But this LED is going to be shining a whole heck of a lot brighter for the same amount of energy input. So we're going to input energy and we're going to get energy out. And LED light bulbs are usually like around 40% efficient. Or what that means is 40% useful energy output. That's pretty good. I don't know about you, but that's dang good, right? That's like a whole 8 times better. So anyways, that's just to give you a little bit of a perspective. So this LED is going to be giving off way less heat than this incandescent light bulb, okay? And every single device does this. If you go up to a TV, what's the purpose of a TV? To give off light and sound, right? You want to see it and you want to hear it. But a TV shouldn't get hot. I mean, that's not the purpose of a TV. The TV shouldn't heat up your house or your room or something like that. Imagine, it's in the middle of July and you're trying to watch a movie and it's 25 or 30 degrees outside or something like that, you don't want your TV to be giving off extra wasted heat because it's already hot outside. You don't need that in your house. Anyways, whatever. Moving on. So we're going to talk, of course, we're going to talk about an equation so that we can kind of quantify how much, right? In the incandescent, 55% useful. In the LED, 40% useful. Jeez Louise. So we're going to talk about percent efficiency, and I'm going to label it as percent EFF. So percent efficiency is equal to the useful output divided by the input times 100%. It's basically just a ratio. It's the ratio or the proportion of how much energy do you put in and how much energy do you get out of it that's actually useful. When we take a look at our data booklet, this equation's in our data booklet as well. There we go. So we see percent efficiency way down here at the bottom. It's just output over input times 100%. Now it's the same thing. It's the exact same thing I wrote down. I just wrote it down in a little bit of a different way. So that's the one way that you could write this. But there are two other things that we could solve for in this equation, right? I see three variables. I see percent efficiency, I see input energy, and I see output energy. So we could rearrange this if we wanted to get input or output. So that's the first version of the equation. Blah. That's the first version of the equation. The second version of the equation is going to be, let's rearrange for input, okay? So if we try and get input, okay, it's our variable's in the denominator. It's in the bottom of a fraction. And so we don't want it in the bottom of a fraction. So it's going to be efficiency equals out over in times 100%. So we want input, so we're going to multiply by in, and multiply by in input, right? And then we got to divide by efficiency. So we got to divide by EFF, and divide by EFF. And let's see what we get. We get left with input equals output divided by efficiency times 100%. There we go. Perfect. So that's our second version of our equation. And our third version of the equation is just if we wanted useful output energy. Okay, if we wanted useful output energy, then we would multiply by input and divide by 100%. So we get output equals percent efficiency times 100% over, percent efficiency times input, input goes up at the top, divided by 100%. There we go. So that's our third version of the equation. Most of the time, we're only going to be doing the first version of the equation, okay? Most of the time, it's just the first version, so there's not that much to worry about. Anyways, let's dive right in. Let's make this video quick. Efficiency example number 1. In a nuclear reaction, a nuclear potential energy of 5.54. This is megajoules. It just means million joules. That's all it means. During the explosion, the energy released was 0.0534 megajoules. What is the percent efficiency of the explosion? Okay, squiggly line. So, in a nuclear reaction, the nuclear potential energy is this. That's the input energy. The input energy is 5.54 megajoules. During the explosion, the energy released is 0. So the output energy is 0.0534 megajoules. What is the percent efficiency? So we use our typical equation. Percent efficiency equals useful out over in times 100%. So we know what our output is. Our output was 0.0534 megajoules. We know what our input was 5.54 megajoules times 100%. So our efficiency, when we put this into our calculator, our efficiency is going to be 0.964%. Now, I'm going to comment about the units here. A megajoule just means a million joules. As long as our units here are the same, megajoules and megajoules cancels out, and we're left with the unit of percent. So as long as our energy unit is the same, or power, I guess, is the same, then we can cancel them out, and that'll be perfectly fine. So here we're going to do another example, and then I'm going to let you do some questions by yourself. A motor which is 60% efficient. So what that means is out of 100 joules input, only 60% of them, or 60 out of 100, become useful energy, right? 40% of this is going to be wasted. Okay, anyways. A motor which is 60% efficient converts 14,000 joules of electric energy into gravitational potential energy and the thermal energy while lifting a 1,000 kilogram elevator car. How much gravitational potential energy would be produced? So what's happening is we've got a motor here, okay, and it's maybe, it's attached to a rope, and there's a pulley up here, and we're lifting a box, and the box is going to get lifted up, okay? And so we're going to put in converts 14,000 joules of energy, and we're going to lift this box up, and it's going to be up here somewhere, and we want to know, well, if we're lifting something, that means we're turning this energy, the input, we're turning the energy input into potential energy. And we want to know how much potential energy are we going to have in the end. Okay, so only 60% of this input is going to get turned into potential energy. I understand it says how much gravitational potential energy, and you're thinking EP equals mgh, or maybe you thought that, but we can't use that, okay? Because it doesn't give us a height. So what we have to do is we have to think about, okay, 60% of this stuff is going to get turned into useful energy. So let's do our squiggly line. Perfect. So our efficiency, as soon as you see efficiency, you know you're going to have to use the efficiency formula. Converts this much into something else. So that means the input is 14,000 joules, and we want to know how much is the output. So let's put down our formula. Efficiency equals useful out over in times 100%. So let's rearrange this. We want out. So we got to multiply by in. We got to multiply by in. Blap, blap, multiply by n, and then we got to divide by 100%, blap, blap, divide by 100%. So the only thing that's left on the right-hand side is output energy. Good. So output energy is equal to input times efficiency divided by 100%. Good. So what is the input? The input was 14,000 joules. The efficiency was 60.0% and divided by 100%. So let's look at this. Percent and percent cancel, and we're going to be left with units of joules. No problem. We can do that. So we're going to be left with a unit of joules. And when I put that into my calculator, we're going to get 8,400 joules of output energy. So that means, remember, our output is our potential energy. So the box will have, or the thing we're lifting, will have 8,400 joules of potential energy at the end. And we could take into account significant digits, so 3 digits. So these are our 3 digits. So we could say, or 8.40 times 10 to the 3 joules. I'm fine with either of those. So just keep in mind, we did rearrange all 3, okay? So this is the one you get in your data booklet. This is how you rearrange for input. We just, right now, rearranged for output, okay? There's the only 3 things you could. We got some questions for you. So there's 4 questions here. Most of them are fairly straightforward. We got the efficiency calculation up at the top. So number 1, a light bulb takes in, blah, blah, blah. It transfers 2 joules as useful light and 28 as wasted heat. Calculate the efficiency. So you got to pick which one of these is useful output energy. Do you want a light bulb to make light, or do you want a light bulb to make heat? I don't know. What do you think? A kettle takes in 2,000 joules of energy. It transfers 1,500 as useful heat and 500 as wasted sound. So calculate the efficiency. Sure, no problem. Some vehicle motors are only about 20% efficient. How much input would be required for the motor to get 1,000 out? So you got to rearrange for input on this question. And then the very last question, calculate the efficiency of a TV which takes in 5,000 and transfers 1,000 as useful light and 1,500 as useful sound. The remaining 2,500 joules is wasted as heat energy. So hint here is, what is the total amount of useful output energy, right? You want a TV to do 2 things, so both of those things are useful. So you're going to have to combine them in a way. So try the questions out. Take a look at the key. Let me know if you have any questions. As always, I'm available between 10:45 and 11:15 every single day for office hours. Even if it's stuff we did a month ago or 2 months ago, right? Let me know, and I am there to help y'all. Have a good day.